comparing means with paired data. I started this in class and I will reiterate and kind of review, and I will then finish the rest of the notes on this video. So we're talking about hypothesis tests, and instead of testing two independent random samples, we've learned that we could maybe group the individuals in each sample and remove some variability. You can group by blocking if you're doing an experiment, and a special type of blocking is matched pairs, or by stratifying if you're doing an observation and you could match in those stratifications. My example in class was looking at two schools that prepare students to take the SAT, and the question was, is there a significant difference between the schools? Instead of just comparing the raw data from A to the raw data from B, or the average score in A to the average SAT score in B, we decided to pair up the top performers in each school, the next top performers, the next top performers, and compare the difference in their scores. A positive difference would mean A school did better than B school. A negative difference, like in this case, would mean that the B school kid did better than the A school kid. And then we took the averages of those differences, and that is called D-bar. And in this case, the average was 22.9. We can then use a one sample t-test because we have now combined two different samples into one list or one set of data, and that's the data of the differences. And if we put that in the calculator, it'll allow us to check our hypothesis. So here's the 5 steps for that. At first glance, it appeared that the true mean difference of SAT scores from the two schools was not 0, so there was some type of difference. And remember, our null hypothesis is that it is 0, and our alternate hypothesis is that it's not 0, or that there is a difference in how well the schools prepare the students. But we want to see if that was just due to randomization variability, who randomly got to assign to go to school A versus assigned to go to school B. We check our conditions. In this case, they claim that the kids were randomly assigned to each school. And then we also have to check our numbers. We would need the number of students at each school to be greater than 30, and in this case they are not. So we will do an NPP. Since the NPP of the differences, we do an NPP of the differences, is roughly linear, it is reasonable to assume that the population of difference is approximately normal. So our conditions check out. And again, you would do this in the calculator. I showed it in class. If you need help, come see me. And we look and we find the probability of getting a difference as big or bigger than 22.9, which correlates to a t-value of 2.49, is approximately 0.0472 or 4.72%, which is small. It's just a little under 5%, but it's still under. So we can conclude that we can reject the null hypothesis and say that there is a difference or a mean difference in the SAT scores between the two schools. We didn't check to see if one is better than the other. That's why we did a two-tailed test, but it does look like they prepare them differently. Now, let's look at it further. What if we did not know that the data was paired, and instead we just did a regular two independent sample test? We wouldn't actually see the difference between the schools. We would get a t-value of 0.31, which is pretty close to 0, and a p-value of 0.7636, or in other words, we'd have a 76% chance of getting the values that we got between the two schools, or I guess we should say the difference in the means between the two schools, assuming that the schools were the same. And then of course the degrees of freedom tells us the shape of our t-curve, and that is found by the calculator for the two independent sample t-test. Basically, we would fail to reject our null hypothesis that the schools were different. We can look at these two box plots to show the three major sources of variability that caused this wrong conclusion. The first is the variability between the schools, and that's the difference in the center of the box plots. For school A, it was 1540. For school B, it was only 1500. The variability of the individual students, and that is given by the IQR, or the range. It's showing how spread out the kids' different scores are. And then randomization of variability, which is what we're trying to check for. When we pair subjects and subtract the scores, the variability of the individual students is mostly eliminated. Okay? Since we are comparing roughly the same ability, we're comparing this smart kid to this smart kid, this second well-performing kid to this second well-performing kid. So we're getting rid of the individual differences. Okay, the only variable left is due to the difference in schools or the randomization, and the hypothesis test allows us to decide if that difference is due to the schools or randomization, i.e. removing the one confusing part of the variability. And doing this increases the power of our hypothesis test, which means we have a better chance to see if there really is a difference in the schools. Remember, power is the probability of not committing a type 2 error. That means accepting the null when it's actually false, or in this case, accepting that the schools are the same, which we would do with a p-value of 76.36%, when actually there's a difference between how well the schools prepare the kids. So to reiterate, the power of a test is the probability of rejecting the null hypothesis given that the null is actually false, so we make the right decision. Now let's talk about confidence intervals for paired data. Again, you can answer the same question, but this time going about it the other way and looking at a confidence interval, trying to guess the actual difference versus doing a hypothesis test to see how likely it is we'd get a difference based off of our sample. So here's an example. To test which acne cream is better, A or B, 100 teenagers with acne problems were recruited for a study. The response variable was determined by the number of new pimples the students got. Okay, let's describe how we could design this experiment so a 2-sample t-test would be appropriate. So this is what we did the day before. We would randomly, that's key to meet our conditions, assign 50 students to use cream A and 50 students to use cream B. We would wait 1 month or whatever time was specified and record the results, i.e. how many new zits or a reduction in zits. And here they said how many new zits. So we're going to remove the reduction in zits, but that's another way to go about it. And then we would find the average new zits for the people using cream A and the average number of new zits for the people using cream B and compare them, which would make our null hypothesis be that the difference between the two averages is 0, and our alternate be that it's not equal to 0. We're just trying to find a difference. In this case, we don't have a hypothesis as to which which cream would be better. Now, if we were to block, okay, or we were to do a matched pairs test, how would we do it? Well, we'd block by acne severity. So the kids with the most acne, the top 2 kids would be paired together, and then we'd randomly assign who uses cream A and cream B to each person in the pair and go down by severity. After, we would then wait 1 month and record the results, etc. Okay, and the question is which method would be best? Well, again, B, but because it limits individual variability. What if, when you're doing this randomness, you randomly assign the kids, just happens to be that more of the kids that have really bad acne end up using cream A, so in the end it looks like cream A doesn't do as good of a job as cream B, but it's just because your subjects had to happen to have worse acne than in the other group. So it limits the individual variability. I'm going to show you one more example. Okay, new homes often come with energy guarantees. That is, the builder guarantees that the cost of heating and cooling the houses will be below a certain cost. And when there is a complaint, the builder will estimate the insulating power of the house by taking temperature measurements inside and outside the house at randomly selected locations, such as inside and outside of a particular window. So they've paired it up. Use a 95% confidence interval to estimate the average difference in temperature inside and outside the following home. So location 1, location 2, etc. So we're going to go ahead and use our 4 steps and look at it.